Welcome back, class. Last week, we learned that the correlation coefficient ρ measures the strength of the relationship between two variables. When we used Excel to calculate ρ for the three explanatory variables in our dataset, we found fairly strong correlations for GR and IN, with ρ's of 0.53 and 0.54. ρ for GE was 0.27, which is fairly weak. In today's class, we'll explore another tool that can help us understand the relationship between a dependent variable and the explanatory variables in a dataset. It's called regression analysis. Regression is a tool for estimating the parameters of the equation that describes the mathematical relationship between the dependent variable and its explanatory variables. The Excel algorithm for doing regressions is called LINEST, which stands for linear estimation. Today, we'll use LINEST to do simple regression. In simple regression, LINEST looks at the relationship between a dependent variable and a single explanatory variable. Here's how LINEST does simple regression on the array with m as the dependent variable and gr as the explanatory variable. LINEST first fits a trend line to the xy plot of the two variables. As I said last time, the trend line shows how, on average, the values of m on the y-axis change as gr increases on the x-axis. LINEST then estimates the parameters of the equation that describes the trend line. We know from algebra how to write the equation for a straight line on a graph having xy coordinates. Here, m is measured on the y-axis and gr is measured on the x-axis. The equation for a straight line on this graph is m equals a times gr plus b. The first parameter, a, is the coefficient or multiplier of gr. The second parameter, b, is a constant. Mathematically, a is equal to the slope of the trend line. Slope is calculated as rise divided by run. That's the amount by which y rises on the y-axis as x runs along the x-axis. To calculate a, LINEST picks 2 points on the line and divides the change in m by the corresponding change in gr. The result is that a equals 1.4. So 1.4 is the coefficient of gr in the equation. The letter b in the equation is a constant. Its value doesn't change with changing values of gr. Mathematically, b is the value of m when gr equals 0. And here, that's 24. Now that we know the values of a and b, we can rewrite the equation for m versus gr like this. m equals 1.4 times gr plus 24. This equation is a mathematical description of the trend line. Now, if m and gr were perfectly correlated, that would be the end of the story. The equation would explain 100% of the variation in m, and we could use it to predict the value of m for any given value of gr with absolute certainty. But that's not true here. As we know, the correlation between gr and m is only 0.53, which means that a lot of the variation in m is not explained by gr. We now ask LINEST to estimate the parameters of the equations for GE and IN. Here are the XY plots, the trend lines, and the estimated equations describing the trend lines. Last week, we talked about explained variation in m, which I referred to as EV. I said that EV is calculated as total variation in m, or TV, minus unexplained variation in m, or UV. This week, I want to conclude this class by showing you, for each of our explanatory variables, the percentage of TV that is explained by the simple regression for that variable. For GR, the regression explains 28% of TV. For GE, the regression explains 7% of TV. And for IN, the regression explains 29% of TV. When we sum these EV percentages, the total we get is 65%. Does that mean that together, GR, GE, and IN explain 65% of the variation in M? Not necessarily. That's only true if GR, GE, and IN are not correlated in any way with each other. If they are, then summing the EVs involves explanatory double counting. For example, if GR and GE are correlated, some of the variation in M that is explained by GR is also explained by GE. The solution to the problem of explanatory double counting when independent variables are correlated is a form of regression called multiple regression. In multiple regression, Lionest's algorithm avoids double counting by estimating a single equation that includes all three explanatory variables. We'll dive into multiple regression next week. See you then.